Bismillahirrahmanirrahim. Okay, so during the last lecture, we have discussed on the magnitude response calculation from the Z plane pole zero location. So we have done it in the last class. If we just make the review, it can be mentioned as that for a particular response or the impulse response of a system, we can find the magnitude response with respect to the zero location and the pole locations, where if you have multiple zero locations, the length of the zero locations, so we need to multiply each of those in the numerators, and in the denominators that will follow the distance from the pole locations, and you need to multiply those things. So we have discussed it with examples in the last class. I believe I have also given one task as a homework. So I believe you have already done that. Okay, so we left this part, how to calculate the phase by using the pole and zero location. Okay, let me choose a different example for these calculations. That means for the the phase calculation. Okay, so this is a general example. Let me draw the Z plane representation. This is the unit circle. This is a 0 and this is a 0, and there is a complex pole like this. Let's say these are the two poles. Now how to calculate the phase of this response or the impulse responses. So the phase of H, you can say Z, according to the formula, the angle. So we have the angle for a particular value of the omega, so at the location of omega equals to 0, so we are targeting this point. At this point, what is the theta value? So in general, let me start with this point. Let put this is omega is equals to omega 1, any value, and for this point we are making these lines from to 0 location, and let me give the name of this one. This is theta 1 and this is theta 2. So whenever we are finding the H, the theta for this one, let's say for omega 1 is equals to this is theta 1 plus theta 2, and divided by not divided by, we need to subtract the other part. So let me write it in this way: theta 1 plus theta 2. So what are the values? You can find it very easily. On the other hand, we have other two values from the pole location. Let me give the value. So this is the x-axis, this is the theta. Let's say this is the theta 3, and try to understand this. This is the distance, and what is the theta value? This is x-axis, so this is the theta value. So this is theta 4. So we have two thetas more, so we need to subtract these two theta 3 plus theta 4. That is how we can find the phase at the location of omega 1. Of course, the omega will change. Since we start with the value of omega equals to 0, whenever we are drawing the phase response, this is omega. So we start with the 0 value, and we are definitely try to draw it up to pi, let's say pi by 2, and then up to twice pi. That is our range of view. So we start with the 0 and we go up to the twice pi. So if we want to calculate at the location of this in the similar fashion, if we want to draw it for omega equals to 0, what will be the value? We can find it very easily. Let me draw it for omega equals to 0, that point. So we are talking about this point. In that case, of course, the theta 1 and the theta 2 both are 0. So we have 0, and also we have 0. These two are for the for the 0 location. And for the pole locations, let me draw it like this. This is the x-axis. What is the theta? This is theta 4. Let's say this is theta 4. And in that case, what is the value? This is theta 3. Or vice versa, theta 3 or theta 4. Minus, this is theta 4 plus theta 3. So this is for the angle for omega is equals to 0 or 0 radian value. So at that moment, what is the value? It will be, this will give you the theta value as minus theta 4 minus theta 3, and that is the result for the location at 0. So it starts with a negative value, and definitely it can start with a negative theta value. Whenever it past the value like pi by 2, at the location of pi by 2, what will be the value? Let me draw it for pi by 2. Okay, so at this location, what will be the value? Again, for the 0 locations, these are the two. So here we have this theta 1, we have this theta 2, so we can find it. And similarly, from the pole locations, we have what is the theta value. So that is the distance, and what is the theta value from the distance of this one. So in this fashion, for each and every value of the omega, you can get a combination of theta 1, theta 2, theta 3, and theta 4, where theta 1, theta 2 will be added, and that will be subtracted from theta 1 plus theta 4 for each and every value of the omega, and you can draw the phase distribution. That means the phase plot for a particular system, where the system was defined as Hz, the system response in the magnitude. When we are talking about the magnitude, this is the symbol, and when we are talking about the phase, this is the symbol. So this is very simple how to deal with the magnitude response, and as well as the phase response for from the z-plane. And I need to be very specific to the concern that the magnitude response and the phase response, mostly for the phase response, this is only true when all the poles and the zeros are inside the unit circle. If that is outside the unit circle, then we just need to calculate according to the formula, not by using the z-plane calculation. So this is only true whenever the poles and the zero locations are inside the unit circle. So this is a note for drawing the pole, drawing the phase outcome for different value of the omega from the z-plane representation. Okay, so at this moment, this is the portion where we have covered the basic understanding of z transform, as well as how to represent it in the z-plane, the pole locations and the zero locations, how we can even interpret the z-plane representation with low pass filter and high pass filter, because you can plot the magnitude response from this plane representation. Now we need to go a little bit further. In the next section, we'll try to understand how to design a very simple filter design by using Z-plane representation or Z transformation as well. So at this moment, if you have any question or any comments or any discussion on the Z transformations or their practical implementation. Otherwise, we can move to the next section, which can be mentioned as the this is I have given the name as the basic filter design. So we'll talk about the basic filter design. As you have already know from your previous experience, so any sort of system actually been represented as a filter. Conventionally, whenever it is in the time domain, it is represented as this. This is called the impulse response. And whenever it is represented in the Z-plane, it can be represented like this. When it is in the Fourier transformation, it can be represented like this, or h e to the power j omega. But sometimes people are also representing h j omega, something like that. Okay. So both are all are the same things. This is in the time domain. This is in the Z transform after doing that one, and this is in the after Fourier transform. So so whenever we are talking about the filter, basically we are talking about a system where this is the impulse response. System means that is the impulse response of that system. So I need your very deep motivation and concentration for this section, because this is the starting point to understand the filter properly. Okay, so I have designed this section with an example, starting with an example. The example stated that we need to consider m-point moving average system. Any sort of system is actually a filter. So you can say m-point moving average system or m-point moving average filter, whatever you can call. And by the mathematical expression, this is the m-point moving average system. As you can understand, we are taking m points from 0 to m-1. So how many points are how many values we are taking? Total n values. So that is x n, that means x0, x n-1, n-2, n-3, like that. And then we are dividing with the total number of samples, that is m. So we are making it average of that one. If we have 3 samples and all the samples have the following values, like 3 plus 2 plus 4, something like that, and divided by 3, that might be mentioned as 3-point moving average or 3-point moving average system. Okay, and I have mentioned that this is one kind of FIR system. We'll talk about the FIR and IIR system later on. Eventually, you understand this. This FIR system represented no feedback in the system. So you don't see any feedback. That means if I have something like this with this system, if I have y n-1, then of course we need one feedback which actually carries a delay from the output. And then the total system actually been converted to the IIR system. We have already learned that in case of IIR system, we have the feedback. It might be a finite number of feedback or it might be an infinite number of feedback, but you have the feedback in case of IIR system. However, in case of FIR system, we just rely on the input values. There is no question about the output or output sequences. Now the impulse response, since this is the system definition, the impulse response, how you can find the impulse response, the input should be given as a delta function, impulse. Input can be replaced with the delta function, and that actually give you the impulse response of the system. So according to that notion, we can say that, okay, this is our impulse response. In any point of time of my lecture, if you have any confusion, so please raise your hand for the clarifications. So we got the impulse response. Now this is actually the system. System actually been defined by the system definition, and from the system definition you can write the impulse response very quickly. And this impulse response actually give you the response of the total system. So according to the time domain sequences, we can draw this Hn like this. It shows that we have what is the value of delta function? 1 multiplied with 1 by m. So all the way you have 1 by m, 1 by m, that kind of stem up to m minus 1. So how many samples you have? You have total m number of samples. So that is the time domain sequences, how it looks like from this mathematical expression to the time domain expression. Okay, now what is our task at this point? At this point, we are looking for the frequency domain representation of this Hn, because that will give us the actual understanding about the filter, whether this is a low pass filter or high pass filter, whatever the case. So we need to understand about the filter. So we need to, our focus is to draw the magnitude response as well as the phase response of this system. Of this system means of this Hn, where Hn looks like this. These are the very practical things. Okay. Whenever we are talking about m point, it is general informate, but you can write 3 point, 2 point, 5 point, 7 point. So whatever the sample number you are taking, that is your task. So you can design your filter according to that. So we are talking about in general m point moving average filter. So from this streamline or time domain sequence, we can very easily write h omega like this. This is your value of x0. That means I should write it like h0, and then multiplied with e to the power minus j omega n. What is the value of n? That was 0. And eventually it gives 1, because this is also 1. In this section, this is h1, because this one, and e to the power minus j omega into 1, the section. Similarly, you can go through and you can write this equation from these time domain sequences straightforward. So now we are in the frequency domain. That means we have done the Fourier transform. According to the Euler's formula, sorry, not Euler's formula, according to the infinite series formula, we can write it, and we have shown it for several times. So from this line to this line, these are just the mathematical manipulations. So you can do it yourself. And after doing that, I'm just taking e to the power minus j omega m by 2, just to make it a format like e to the power j omega m by 2 minus e to the power minus j omega m by 2. So e to the power j theta minus e to the power minus j theta, in that format. So similar to the denominators, e to the power j theta minus e to the power minus j theta, so that we can convert it to the cos format or the sine format. So that is our target. And from this equation, we can write it directly to that one. where you can see this part actually been converted to this sine omega m by 2 divided by sine omega by 2. So you know that the equation according to the Euler's formula, the sine theta is equals to e to the power j omega minus e to the power minus j, sorry, I should write theta, j theta minus e to the power minus j theta divided by twice j. So this is the formula. By applying that formula, you can come forward from this equation to that equation, where we have 1 by m from there, and this one can be written like this, and as I have already mentioned that this one can be written like this. Okay, so we have 3 parts in this equation, so need to be very specific, and we need to understand each and every part of this equation. In the left side, we should write h omega. So this is the equation. In this equation, we have both the phase part and also the magnitude part. So first of all, this part 1 by m, that is a constant. So there is no relation of the phase with 1 by m. That is a magnitude, and it remains a constant value. For m, what is m? M point. So it can be 3, or it can be 5, it can be 7, or it can be 4. So it is a value. It is a value. So 1 by some value. So it is a constant. It will remain constant. And in the last portion, this portion, it actually carries the phase. Where is the phase? That is, the phase value is minus omega m minus 1 divided by 2. That is the phase. And of course, it depends on both the value of m, where m is a constant for a particular case, and omega is a variable. So this shows the angle or the phase. This part only shows the phase. There is no portion of the magnitude. The magnitude is 1. So eventually that actually multiplied with 1 by m. So there is no question about the magnitude. So what I'm mentioning, this part only carries the magnitude, and this part only carries the phase. What about this? This actually carries both the magnitude and the phase. How? Whenever you are putting some value, let's say m is a constant, but you are changing the value of omega with with these divisions, you are getting some magnitude. And definitely whenever you are changing the value of omega from 0 to, let's say, pi, for all the values, of course, this magnitude, the amount of this value, the magnitude will definitely changes. On the other hand, what will happen? The sign of this signal, the sinusoidal signal, it will changes after 180 degree. So after 180 degree, that means after pi, it will also change the angle. So what is actually phase? So it shows that it also shift the angle after 180 degree. So that means it has the impact to the phase as well. So this component has 2 impact to this h omega. One is the magnitude. It also make the impact to the phase as well. So with the plot, you can understand more about this. So you can remember this equation, h omega is equals to this. And now we'll move to the plotting of the magnitude part. So if we concentrate on the magnitude part, we do not need to consider this, because there is no magnitude. So we are considering only this part. So if you are considering this, okay, so this is our part for the plotting. And as you already know that for omega equals to 0, this is our magnitude plot. So we are looking to this. this x-axis shows, y-axis shows omega, the magnitude. At omega equals to 0, of course, 0 divided by 0, so it makes infinite, undefined. So that's why we move to the L'Hopital's rule. And then we can find that, okay, for omega equals to 0, the theta is very small. So sine theta is theta and sine theta is theta. So from there, you can find the value is 1. So at omega equals to 0, you are getting the value is equals to 1. Fine. For other case means for other value of omega, you can just put the value of omega there and you are getting this kind of sinc function. Of course, this is a sinc function multiplied with 1 by m. That's it. So we know about the pattern of the sinc function, the black line, now it's converted to the red line. It shows the sinc function. And definitely it moves to the infinite range. As you know that the sinc function is an infinite range signal. It can carry all through the value up to the infinity. Now try to understand that whenever we are putting a bar like this, that means we are talking about the absolute value. That means we are talking about the absolute value of this one, because it is always a positive value, 1 divided by m. So we are basically reflecting the absolute value of sine theta over sine theta. So as you can see that from this black sinc function, so it moves to the negative portion in some point. And we have found that this point is like twice pi divided by m. At that point, it actually moves to the negative. So whenever we are talking about the absolute value, this negative value moves to the positive value. Of course, it moves to the positive value. Now the question is why we are talking about the absolute value. We are talking about the filter. So the filter, what does the filter actually do? It actually it will pass the signal or it will block the signal. Whenever there is a negative value, it actually shows that it is the phase. Negative value means it shows the phase. But what about the amplitude? For a particular frequency, let's say the amplitude is this. What does it mean? Let's say the amplitude is A. It shows that for particular that frequency, omega 1, all the value will be amplified with the value of A. If there is, for a particular value of omega 2, if there is a negative value, negative B, let's say negative B, it doesn't mean anything, because conventionally, what does actually it makes? It makes the magnitude be positive in case of the particular frequency. That means the amplitude of, for a particular value of the frequency or omega, the amplitude is always a positive. Amplitude is positive. You are amplifying or de-amplifying, whatever the case, that is a positive, but it might be shifted to some places. That means the phase might be changes. The phase might be changes, but the amplitude is always, with respect to something, you have the amplitude positive. What does it mean? You have the frequency component omega 1, or you don't have the frequency component omega 1. You have the frequency component omega 1 means that omega 1 multiplied with 1. So you want to pass it. Or omega 1 multiply, you don't want it. Omega 1 is multiplied with 0. You are actually blocking it. Or you want to fade it out, omega 1 multiplied with 0.003. So you are actually fading it out. In all the cases, you are multiplying your signal with the positive value. There is no negative numbers you are taking. So that's why it is always convenient that in case of magnitude response, we are taking the absolute value. And sometimes we are taking the square of that. so that all the values actually moving to the positive one whenever we are talking about the power spectrum of the filter. Okay, we'll talk about this later on. First of all, we need to understand why do we put magnitude response the absolute value. Why do we are taking the absolute value? Because logically we need to take the positive values only, not concentrating on the negative value. So then conventionally this magnitude response should looks like this red line only. Okay, now the second thing is from this perspective, when this change actually been happened, so suddenly you are getting some change. What kind of changes? Actually it was like this, you are moving to the upwards. So what you are doing mathematically, you are multiplying each and every point with a -1 value. You are multiplying. So let's say it was -0.5, you are multiplying -0.5, you are multiplying with the -1, then it is equals to 0.5. So mathematically all the points are actually being multiplied with a -1, and then that actually moving to the plus value. So it moves to the positive value. So all the way you are multiplying with a -1 value. You can understand in a way -1 in the magnitude or amplitude, it actually been reflected to the phase as 180-degree phase shift, -1. For example, if you have a current like this in this way, if you want to shift it in the opposite direction, you need to multiply it or add it with an angle with 180 degrees. So you need to add 180-degree phase shift, and then the direction will be changes. So in case of a magnitude, you need to multiply it with a -1 for this kind of magnitude response. However, for the phase response, you need to add 180 degree. Suddenly, you need to add 180 degree for the phase shifting whenever we are talking about the phase shifting. Now we are looking for this point, try to understand where are those points. Let's say at this point, definitely the amplitude is what? Amplitude is equals to 0. So from that perspective, we can write, as you can understand, this magnitude actually depends on this part, and the zeros basically depends on the numerators. So we can put this sine omega m divided by 2 equals to 0, where it would be equals to 0. For which value of m, omega, it would be 0. So from that perspective, we can find that for omega equals to twice k pi divided by m, we got the zeros. For example, now for value k is equals to 1, we have twice pi by m. That is the first point. And if you can concentrate on this magnitude response, we can find, yes, this is the first 0 at twice pi by m. The second one, for k is equals to 2, we have 4 pi by m, and then 6 pi by m, and so on and so forth. But if I ask you one very simple question, how long we should proceed? The next one, definitely it should be 8 pi by m, then 10 pi by m. So how long we should go? We should go up to what? Up to pi, because pi is our range of view. If you can recall, pi is the range of view. So let's say if m is equals to 5-point moving average, 5-point moving average, then what would be the highest value in this case? This is twice pi divided by 5. So then 4 pi divided by 5. Still, I believe that this is of course less than pi. Then whenever I have 6 pi by 5, definitely this is more than pi. So we shouldn't go to that region. So we can stop in between this. So always the magnitude response should be starting from omega equals to 0 up to pi, where for m is equals to 5, for 5-point moving average, we are getting the first 0 at twice pi divided by 5, the second 0 at 4 pi divided by 5, and the third 0 maybe 6 pi divided by 5. So we need to neglect this. We are not going to that. So eventually we are getting the diagram like this and like this, and you need to finish it over. So always we need to move the omega from 0 to pi. That is our range of view. And that is how we can find the magnitude response. Okay. Yes, 132.
So, sir, the maximum value of k will be up to m.
The maximum value of
K.
m. Okay.
K will be up to m.
No.
If it goes beyond m, then the omega value will go beyond pi.
Actually, from this example, I have shown that example afterwards. For m is equals to 5, actually we can take k is equals to 2, and that is the maximum. Because in that case, we have twice pi divided by 5 and 4 pi divided by 5. In this case, k is equals to 1, and in this case, k is equals to 2, because in general, the equation is this for the zeros. So that means,
so, sir,
yeah.
k will be then less than m by 2.
Exactly. But to be very specific, that is m divided by, in this case, m divided by 2 and the lower ceiling. What is m divided by 2? 5 divided by 2, that is 2.5, and the lower ceiling of that shows 2. That is the value of k. Okay.
Yes, sir.
Okay, thank you. So we'll talk about this. So your friend is already asked some question. We'll discuss in the subsequent section. Okay. So we have plotted the magnitude response. That is very simple, but we need to just understand each and every part. Now comes to the phase plot. Before understanding this expression, I would like to show the magnitude plot first of all, the phase plot first of all. Okay, the question your friend asked to me, that is the thing, what should be the value of the k, or the range of the k. Of course, for k is equals to 0, we need to neglect that, because at that moment, of course, omega equals to, this is omega is equals to twice pi k divided by m. So for k is equals to 0, it is omega equals to 0. Okay, can you hear me?
Yes, sir.
Okay, so probably we lost the connection for a few seconds. Okay, we have the recording still, so let me share the screen again. Okay, so I'm not exactly sure where we have concluded. However, I can start with the things. The phase plot, we have already done the magnitude plot, and now we'll talk about the phase plot for this m-point moving average. So your friend already asked the question, what should be the range of the value of the k, the highest value of the k. So as we can already establish that the omega should be 0 at the location of twice pi k divided by m. So for k is equals to 0, omega equals to 0, but it is not possible, because we already understand that at omega equals to 0, we have the highest value. So the k equals to 0 is not possible. Then for k is equals to 1, yes, we got that. This is practically, this is twice pi divided by, for the 5-point moving average, this is 5. Then for k equals to 2, we have 4 pi divided by 5, and we'll take that. for k is equals to 3, we have 6 pi divided by 5, and we can't take that. So we found that the maximum 2 is the value. So then if we want to make a relation between m and k, we can go for this. What is that? M divided by 2 and the closest less value, less than the lower ceiling, you can say the lower ceiling of that. If that is a 5-point moving average filter, then 7 by 2, that is 3.5. So that means the highest value of k is equals to 3. In that way, you can find the value of k. Okay, now just concentrate on the phase response and the magnitude response side by side. Okay, so this is for m-point moving average, where m is equals to 5. Okay. In case of magnitude response, where we'll find the first 0, of course, at the location omega equals to twice pi divided by m, which gives the value 2 pi divided by 5, and that is equals to 0.4 pi in the scale of pi. If you want to make it, let's say, divided by pi, that is called, what is the value of omega? What is the name of the omega? We call normalized frequency. Again, if we normalize that frequency with the pi, then the scale is starting from 0 to 1. In many literature, we are using this kind of notion like 0 to 1, the scale 0 to 1. Don't be confused with that. Of course, this 1 means pi in the omega scale, and divided by pi, it gives the value of 1. So here 0.4 pi actually means 0.4 here, because we are dividing the whole scale with respect to pi. Okay, fine. Now in the phase, what is the phase value? What is the phase value? If you go to the, if we move to the upper one, we'll find that, let me go to the actual equation. What is the phase component? Where is the phase component? This actually shows the phase component, where the phase value with respect to omega is equals to what? Minus omega m minus 1 divided by 2. So that is the value of the phase. So if we consider with this phase and plot it with respect to omega, how it looks like for 5-point moving average. Okay, we are at this point. Okay, let me erase this part. Okay, yeah, fine. So now for omega, what should be the first value? The omega is definitely 0. We can find it there, and this is a linear equation. This is a linear equation where you can write it like this: minus omega. What is the value of m? M is 5. 5 minus 1 is 4. 4 divided by 2 is 2. So we can write it 2, or you can write minus 2 omega. That is our phase with respect to omega. So that is definitely linear. That is a linear equation, of course, a linear equation. Now for omega equals to 0, you'll find 0. For omega equals to 0.02, for 0.02, you are getting this point. 0.01, you are getting this point. And of course, there is a negative value. That's why it just goes down in the negative value. It increases with the value of omega. However, since there is a negative value, it will goes down up to 0.4. Try to understand this point. This is very important. Up to 0.4. Then what happened? In case of, if you can recall, in case of magnitude response, actual value was like this. But suddenly we are multiplying all the points with -1. And that is equivalent to 180-degree phase shifting. 180-degree phase shifting means you need to add 180-degree with that value, and that is the sudden change of this theta. And it is suddenly we are adding 180-degree. Why? Because we are multiplying -1 in all the cases. So that's why in all the cases we are for this phase, what we need to do, we need to add 180-degree. And where to do that? At the location, at the same location, at 0.4. And then again you are increasing the value of omega. Omega equals to 0.6, omega equals to 0.7, omega equals to 0.8. So stop there, because at 0.8, again you have a 0. Whenever you have the 0, you need to add again 180-degree. So you are adding 180-degree more, and then you are increasing that value, increasing the value of omega, and whatever the value you are getting, and you need to proceed like this. And afterwards you just, fortunately you are at 0 location. Not necessarily you need to go to the 0 locations all the time for all the system. Okay, if I recap the things again, what we have done, in the phase response we are doing like this. Whenever we have the change, we need to add 180-degree. We are doing like this, and whenever we have this change, we have 180-degree shift, and this is called the folded version of the phase response. Of course, there is a folding, so we are folding the things like that. So that's why it is called folded version. Sometimes this is can be also mentioned as unfolded. No problem with that. But you can understand that sometimes it makes difficult to understand or represent in the thesis paper or in the book. It takes actually a huge area to represent this kind of thing. For example, in this case, this is very simple, but if that is a very complex one, sometimes it takes a longer space or very wide space to represent the phase response. That's why researchers are always interested to represent it in the folded version. Okay, so is that fine? So this is the folded version. So of course, the theta, we have already mentioned the theta of omega is like minus omega m-1 divided by 2. Divided by 2. Yes, that is the value. But how we can present this 180-degree shift? How we can present this 180-degree addition and with a particular moment? How we can add those? So to incorporate those things, 180-degree and with a particular moment, so we can represent the equation like this. Please concentrate on this point. So this is our phase we are talking about, minus omega m-1 divided by 2. So that is our phase response. And now in this part, what we are doing in this part, we need to add pi. So let me write it like this here. Let's say minus omega m-1 divided by 2. We need to add what? Pi. When? We are writing at the location of, let's say at the location of twice pi divided by m into k. At that location, we need to do that. So that's why we are putting a unit step function of omega minus this. For which value of k? starting to the value of, we are putting k is equals to 0. You can neglect this k is equals to 0. You can even put k is equals to 1 to m divided by 2, the lower ceiling value. What does it mean? If you draw, if I ask you to draw, please draw u omega minus twice pi divided by 5 for 5 moving average filter k. How you can draw this? Of course, this is in the scale of omega. So after twice pi by k, where k is equals to 1, 2, 3, where k is equals to 1, 2, 3. So let me draw like this. K is equals to 1 to some value. That is m divided by 2, lower ceiling, that is 2. 1 and 2. You got a stem. In the time domain, how it looks like, I'm drawing this unit step function, where we are getting the stem at k is equals to 1. We are getting the first stem. We are getting the first stem. What is the location? This is twice pi by 5. This is omega. What is the second? Where is the second stem? At k is equals to 2, we have the second stem. That is 4 pi divided by 5. So those are the stem. And then that stem is multiplied with pi. Now, what is the value there? What is the value? 180. So 180 is the value. 180 is the value. And they are adding with our minus omega m minus 1 divided by 2. That means it actually proceeding like this. That means there is a negative value goes like that. Whenever it reaches to that omega value means this twice pi by 5 at the first time, then it will be added with 180 degree and then jump like this. And again, it will proceed like this. Whenever the second k, that means this second stem came over there, then it will jump again 180 degree. And that is how you can represent the phase response like this. I still believe that you need to concentrate on this equation more closely, but I have already discussed these things. Probably you can see this equation more closely and this video lecture once or twice to understand the process. However, in practice, this is very simple. This is very simple. Whenever you got a 0 crossing or touching, in that moment, you need to add 180 degree, and that's it. Why that is so, I have already discussed those things. One more thing I should discuss here. From the magnitude response, you can't say that whether this is a FIR filter or IIR filter. It's not possible to say that. But by seeing this magnitude response, can you say what kind of filter is this? What kind of filter is this one? Any of you?
Low pass filter, sir.
Yes, of course, low pass filter. Thank you for your response. This is a low pass filter. Fine. From the phase response, you can't say whether this is a low pass filter or a high pass filter or band pass filter. From the phase response, we can say, we can comment on the type of the filter from the perspective of FIR or IIR. In case of FIR filter, this phase response is linear. And you can see that the phase response is equals to minus twice omega for 5 point. For m is equals to 5, it was like minus twice omega. That means this is a linear phase filter. If this is a linear phase filter, non-linear phase filter, let's say if I put omega square for a hypothetical example, of course, this is a non-linear phase filter. So from the phase response, we can see that this is a linear phase filter. So it is of course a FIR filter. We can justify that this is a FIR filter. If that was a, let's say, nonlinear filter, for example, I'm giving one nonlinear filters like that. So this is a nonlinear. Then of course you can go 180 degree nonlinearity, then 180 degree maybe nonlinearity like this. Okay, so this is a, from the phase response, I can say that, okay, of course, this is an IIR type filter. And that makes some problem. In future, we'll discuss about this nonlinearity. This is a great disadvantage of the IIR filter over the FIR filter. So that's why people are always choosing the FIR filter for precise filtration. From the IIR filter, it's not possible, or you can say it's difficult. You need another filter called all-pulse filter to rectify this problem. Okay. So at this moment, do you have any confusion or any part do I need to repeat for your understanding for the magnitude? So the steps I can recap. Where to start? The first of all, you have the system definition. The system definition was like this. This is your yn is equals to x n minus k, where k is equals to 0 to m minus 1 and averaging. So that was the system definition. What the system actually do, it adds m number of samples. You have the m number of samples, you are adding those, and then you are dividing with that number m. That is the m point moving average filter. Very simple. From there, you can find what is the impulse response of this. Of course, the impulse response of this, you need to replace your input with a delta function, so delta n minus k. From there, you need to find what is the frequency domain representation, the omega, how it looks like. From there, you can find h omega magnitude and you can find h omega phase. You need to understand two very basic things for h omega magnitude. Always the magnitude should be in the positive direction. And the second thing is where to stop. You should stop at the location of pi. You are not allowed to cross the value of the pi. Then if you want to cross that, you are actually spoiling the things. Because in the next section of our understanding, when we'll talk about the discrete Fourier transform, we can always see that we will take this like the representation are like this. That means up to twice pi, where of course from the pi to twice pi, it is a replica from the 0 to pi. That's why never cross the value of the pi. That is a very fundamental concept of the magnitude response. Number two is from the phase response. For our case, the phase response is a negative one, or it can be negative or positive. So we should go like that. And whenever we have the crossing in the magnitude response, we need to jump 180 degree shifting, and then we'll move again. If there is a crossing in the magnitude response, we need to cross again 180 degree, and we need to stop again. We need to stop just on the pi value of the omega scale, in the value of the omega scale, or in the scale of omega by pi, it is representing 1, 0 to 1. Don't confuse with this value like 1 or pi. So from that, so anytime whenever you are seeing this 1, you can take that, okay, that is in the scale of omega divided by pi. Okay. Okay, so maybe we can start the filter in the next day. I believe that this is enough for today. because in the filter section, we can proceed a bit more whenever we'll start with this, inshallah. Okay, so do you have any question or comments at this moment? Looks everything is fine. So let me stop the session. Thank you for your presence.